it's 9:35, so let's start. So welcome everyone and thanks for joining this workshop. So this is we are almost at the 2 years progress of ACHIEF progress. And so the global thematic of this workshop is boosting high performance materials for energy intensive industries. And we will present you the progress of the project and the scientific results that we have up to now on the different thematic of the project. So first, to start, the first question is what ACHIEF name mean? So this is innovative high performance alloys and coatings for highly efficient intensive energy processes. So it's a European H2020 project that has been funded by the European Commission under the grant agreement number 9583/74. So for today, the agenda of this workshop. So I present myself, sorry. So Marie Cabaret, I am working at CEA and I am the project coordinator. So I will start with this introduction and global presentation of the project. Then we will switch to a presentation from Tom Anderson from VTT about the artificial intelligence for the material selection. We will then have Sébastien Vry from CEA that will speak about PDC coatings development with improved high temperature corrosion and erosion resistance. As a third topic, we will have Pilar Ray Rodriguez from AMEN that will present the topic about innovative high temperature and creep resistance materials based on HEA's models. Following this subject, we'll have Lorena Caliero from Tecnalia that will present the result for advanced chromium steels with 15% improved creep resistance and high temperature corrosion resistance. And then we will finish not with Andreas Polkotter, but with Britta Kor from Engineering Group that will present sensors developments with the liability to withstand harsh environments. And then we will finish this meeting with some conclusion and the next step at around 12. So once again, do not hesitate to write your question in the chat of the Zoom tools and to have an interactive presentation. And on the schedule, there is always some times accorded to questions after the presentation. So here you have next pictures of our speakers, so Tom Anderson, Sébastien Vry, Pilar Ray, Lorena Caliero, and so not Andreas, but Britta Kor. So to give you a global overview of the project, so as said, it is the H2020 project, which is coordinated by the CEA, so Commissariat à l'énergie atomique et aux énergies alternatives. The project is grouped 11 partners from 6 European countries, and it started 2 years ago, the 1st October of 2020, and it will finish in about 2 years in March 2024.
Marie, yes, sorry to interrupt, Marie, but we cannot see the slide moving, so.
Yeah, it's an issue. Okay. Do you see them now?
Yeah, we can see it now. Yeah.
Okay, we'll keep like this. Okay, so the 11 partners from ACHIEF are Amen, Constellium, Angenic, VTT, Tubos Tornadoes, Synthesis, Tupras, Technalia, ArcelorMittal, and P&O. So to give you an idea of the challenge that ACHIEF have to face. So it's in the field of the energy intensive industries. So in terms of positive industrial field sector, it represents about 6.3 million jobs for the Europe, and about 20% of the European GDP. However, it's a very high energy demand, about 1/3. It represents of 40% of the global CO2 emission, and also 15% of the total of the European Union CO2 emission. So the goal is really to decrease the different challenges is to decrease the energy consumption and the CO2 emission of this high energy intensive industry sectors. So what is the concept? The goal is to improve process performance and energy efficiencies in this type of industries by developing more durable materials, components, and equipment. So how the project has been defined. So at the first step, to implement novel integrated artificial intelligence aided materials toolbox, to define, thanks to artificial intelligence simulation and models, some candidates of innovative materials, to develop them at lab scale. So it will be efficient materials, but also coating solutions. To validate them with 3 different use cases under aluminum, steel, and petrochemical sectors, and then to promote the result and to disseminate the results of the project of ACHIEF. So what are the different objectives, and so the different materials of this project is to develop models for materials designed based on computational modeling and artificial intelligence. Following this first step, to develop novel protective, so polymer-derived ceramic coatings with improved high temperature erosion and corrosion resistance. To develop innovative high temperature strength and creep resistance materials based on novel high entropy alloys to allow reaching higher process temperatures. To design new high chromium steel grade with creep resistance of 15% improve. And also to develop temperature and strain fiber bragg rating sensors to be embedded in the components fabricated with HEA materials or coated with PDC coating to follow the life of the materials. And then to demonstrate the the performance, and the efficiency of the different materials and coatings in the 3 different use cases, as said, in petrochemical, aluminum, and refinery. So here is the work plan of the project. So it's divided in 3 work package where we develop at lab scale the different materials, with in parallel some iterative communication with the work package of models and artificial intelligence. Then we develop in the work package 6 the sensors to be embedded in the pilot scale use case, and then assessment of the whole fifth work package at industrial case. So the global value chain of the project is at the first step, so to develop the digital tools by VTT and Heyman at the beginning, then to develop at Heyman, CA and Technalia the different theoretical and at industrial and at lab scale materials. To develop them, to develop the process of application of these different materials, to apply them on the different substrate, and then to apply them in the different industrial plants. So the project started at TRL 3.4 in terms of material development, and the goal is to validate both technology but also materials at TRL 5, meaning in a relevant environment. And so with all this work, the expected impacts are the improving the energy efficiency by 30% in the different use case, reduce CO2 emission by 20%, and also to increase the equipment lifetime of more than 20%. So I am going to give the speech to Tom, sorry, who is going to present you the artificial intelligence part of the project. Thanks.
Yeah, hello.
Yeah.
So, good morning, everyone. You can see my screen now.
Yes.
Yes, okay. So, my name is Tom Andersson, and I'm from VTT, and I will present this artificial intelligence tools for material selection task. So, briefly, the content for this presentation is first go through the use case, then tell something about these high entropy alloys or complex concentrated alloys, and then describe the design approach for these alloys, and then the workflow, and after that some few slides briefly on what will come after the alloy design phase. So the use case here that I will present in this, where the material selection is aimed here, is this kind of a component or insert component in this steel furnace. So basically this kind of a star component that is used to hold these tires in place and in correct form or correct stance, so that the other components wouldn't wear down and the actual process would work properly. So the main goal is to decrease the repair damage of these different components and the cooled water consumptions by improving the strength or high temperature strength and creep resistance of this part or component. So in brief, what is these high entropy alloys? So basically traditional alloys are these based on this one element that is mixed with a small amount of other components to gain strength and different properties. But in these high entropy alloys, we have usually more than 4 to 5 principal components or main components that are mixed together in a in this kind of a mixture that usually are in the different phases. So basically the phases are either solid solution or intermetallic or even amorphous or some mixture of those. And why we decided to come to this, so basically many times these high entropy alloys or these complex concentrated alloys, they have higher strength and yield properties than these more traditional alloys, and often they are more usable in higher temperature or higher temperature ranges. And for this use case, we end up with this kind of mixture of PCC and FCC metal that should have this kind good portion of this kind of high strength and quite high ductility. So it should be quite good for these application. So the challenges here is that these high entropy alloys don't really follow the empirical or traditional rules for this metal selection or metal alloy design, and also there are a huge number of different combinations. So these kind of traditional tools to select these alloys are usually either really time consuming or they don't actually work. And what else we could use? So basically this atomistic simulation or ab initio simulations. But then again, there is this availability of different potentials. So basically the rules how these different components act together, they are lacking. And also these methods need quite powerful computers, and the computing times are usually really long. And we could also do this kind of parametric approach, but this is quite new group of metals, so there are not that much information or literature and knowledge about this. So that's kind of not good. And also this kind of Galfat type of tools could be used, but then again, as this is quite new type of materials, there are limited databases for this, and also the time and cost are affecting this. So the main method here is to train this kind of machine learning tool on neural network that is used for the design of these materials. So first we need to develop a database that can be used as a training and data for this neural network, and then we can use this network to synthesize or come up with different candidates materials. And after that, we need some tools to validate the candidates, so we could be relatively confident that they are usable in this environment or this environment for this use case. So the database for this neural network is based on literature survey. So, and for these different traditional features or traditional high entropy alloy and design rules. So meaning mainly this mean atomic ratio, average melting temperature, mixing enthalpy, electronegativity, and valence electron concentration, and mean bulk modulus, and the standard deviation of those, and also this mixing entropy and Young's and shear moduli are used here. So these parameters are searched from the literature for different alloys, and then used to form this kind of a database to train the neural network. So basically these 15 features, the number of elements, so usually more than 5 elements are needed so that we can call this alloy as high entropy alloy. Mainly more than 4 or 5, and usually those concentrations should be quite close to equiatomic, so meaning that there are not one element that is constituting the majority of the whole alloy. And then third parameter was this kind of phase, so whether the material is amorphous, intermetallic, solid solution, or some mixture of these intermetallic and solid solutions. And finally, we have decided to use these 78 different chemical elements for this data set. So basically this kind of adversarial neural network is used, where we have this generator and then this discriminator, and they are trained so that the generator will generate candidates that this discriminator cannot anymore describe to be fake. So basically we would come up with this real-like alloys or real-like candidates. These neural networks both have two hidden layers, and as said, these parameters are used that were basically mentioned before. This seems to be quite, or needs to be quite, or will level quite fast. So basically these training epochs or training cycles don't need to be that many. So this, in that sense, this seems to be quite fast to train. And as a validation method for these alloys that the generator generated, have this kind of a data sets and material databases are used. So basically first, this data set that has been generated has been compared with this materials database that has found. So to see that the data set used, or the phase used in the data set, corresponds with the materials database that will be used to validate the neural network candidates. And then finally, this neural network candidates are compared against the molecular database, materials database found from open sources. And for that, it seems to be quite well predicting the phase for these different alloys. This tool, has been made, or this tool has been made, and it will be made public during this project. And there is also option to come up with this polymer derived ceramics that will be the topic of the next talk, but I will not go those through here. So the parameters of the dataset used for that are a bit different, but the neural network works the same or similar way as for these high entropy alloys. So screening for the simulation, as mentioned before, first approach was to use these 78 chemical elements that are not noble gases or are not radioactive. But when we made a bit more survey for this, we came up to also exclude these toxic elements, so that material production would be more safe, and also that the final component would be safe, and also exclude these expensive elements, so that the actual part that will be produced with this material would not be that expensive and would more likely to be usable in this application. Also, these elements that have high melting temperature were removed due to the manufacturing limitations. So basically, it is a bit the consortium didn't have capabilities to atomize these elements that have really high melting temperature. And also these rare earth elements were excluded from this second screening. So this we ended up with 19 different elements, and for those also there are quite numerous possibilities for different alloys. And also this further limit constrictions for this were decided to on the basis of prior experience, and also this different what kind of the materials are usable for this kind of a use case. So we decided to emphasize these nickel alloys that has nickel, aluminum, and silicon, and also this kind of a limitation that no more than 35% per individual element is included or in the alloy. So finally evaluate the results. So there were a long list of different components or candidates produced with the scan, and we made this fast screening for those with this thermocalc or this Calfat tool. And for that solidus and liquidus temperatures were a bit different than for this rule of thumb that was used for this training for this neural network. So the list was shortened quite much. So we decided that these materials, so the solidus temperature for this material should be more than 1600 kelvins. This is since the application temperature or the use case temperature might be up to 1150, so there should be some tolerance to the actual solidification temperature, so that the materials still have some strength left. And also we had to neglect even some more elements, since the database that we used for the evaluation of these materials didn't include every single element that was left first in the selection. And also after we did this fast screening, we computed the phase diagrams for these materials to see that there are some phases that are known to be beneficial for this, and for many of these candidate alloys the phase diagram was really messy, so we decided to neglect those, so that the final alloy would have, or we would be relatively confident that the final alloy would have the phases and that are more usable for this kind of applications. And also this boron and carbon was decided to show that if the alloy has any of those, they should only be as a minor alloy element. And also this cobalt in this was excluded, since it might cause some health issues. So as was said, so basically these two approaches, so to do two different neural network candidate sets, one with that 78 different alloys elements, and the one with 19 different alloys were analyzed with this method. But some of the candidates had to be, or some of the elements had to be removed from the candidate. So we modified the composition a bit so that they could be analyzed with the thermocalc. And we finally ended up with this candidate alloy that has 4 components. So it would be this complex concentrated alloy in this case, or medium entropy alloy. And it seems to be quite promising, since there are quite high amount of FCC, or this gamma prime type of phase that is known to be beneficial for these high temperature alloys. And also there seems to be this kind of BCC B2 type of mixture there. So we would end up this kind of a dual phase material of FCC, BCC, and we are aiming this heat treatment so that we could form this gamma prime phase mixed with this BCC B2 phase that seems to be, according to literature, quite good for this, or have quite high strength. So after that, when we synthesize the material and produce it with different methods, so these two different 3D printing methods, laser sintering and this direct energy deposition are used here. So when we have those and do the characterization for those, we can produce these synthetic models to analyze the behavior of the material in this environment. So basically we scan those materials with EPSD or do the EPSD characterization for those and take different statistics out from the EPSD analysis and build on this kind of synthetic element or synthetic model based on those. And also we need to do some testing for those, so basically tensile testing, and then we will do some creep testing for those to come up with the material properties or calibration data for these microstructures. And also we need to decide based on the characterization what kind of models we use, so basically which different deformation mechanisms are used in this alloy, so basically how complex model we need to have to be able to capture the behavior of the material. And here's an example of these how these different parameters affect our temperature and grain size effect. So in this case, this kind of single crystal model is computed to see how, for example, temperature, what kind of effect temperature might have, and also the grain size in this. And also one example, so basically when we have the material calibrated, we have done a bit similar analysis before. So in this case, we played with the aspect ratio of those prior austenite grains or the grains. So basically how elongated they are or how round in principle they are and how that affects the load carrying capacity of the material. So this similar kind of analysis will be done for this in the future also. So thanks, that was in brief what I have had in mind.
Thanks, Tom. Do we have any question? Okay, so we give you again 2 minutes, and I propose then we switch to in 2 minutes at Sébastien Vry presentation on PDC.
Okay.
Okay, Sebastian, you can start.
Okay, is it working? You can see my screen?
Yes.
Okay, thanks. Good morning, everyone. Thank you for attending this workshop. My name is Sébastien Vry. I am leader of work package number 3, and I am working at CEA. It's the French Research Center in Grenoble. The main objective of this work package is to develop anti-corrosive coatings using polymer-derived ceramics. This kind of coating should be easy to apply and low cost to an industrial scale application. Firstly, a task was to assess the characteristics of the elements that would make up the formulation. The main objective to have a high temperature and wear resistance properties. The second task concerns the work on the development of the formulation and the determination of coating processing parameters. The third task is in parallel of the second one and is about the identification of the relationship between the composition of the formulation, its processing, and the properties that lead to high temperature resistance into melted aluminum. There is 2 partners involved in the materials to be protected. The first one is Consortium. It is known for its aluminum products. For this partner, 2 use cases are targeted. The refractory bricks, as you can see here on the left side.
Sebastian, your slides are not changing.
Okay, this is the same problem as you. Sorry. This is fine like this?
Yes, it had changed on the third. Yes.
Okay. Sorry for this. Okay. So I was saying that consortium partners got 2 materials targeted. The refractory bricks on the left side that conveys aluminum, and the second material is to protect is graphite rotors that are immersed into aluminum bath. These rotors allows the purification of the aluminum bath with the injection of gas into it. For this one, this lead to the impurities going up to the surface. The difficulty are the adhesion and wearing caused by aluminum on refractories. The melted aluminum temperature is slightly lower than 700 degrees, and for the case of the graphite rotors, they are impacted by the oxidation in air at the surface of the bath. The objectives here are to reduce defects of the rotors caused by oxidation and to lead to the aim of reducing the replacing frequency. Consequently, it would lead to an increase of durability. The second partner involved is Tüpraş. They are known as the leader of petroleum refinery in Turkey. They face a problematic of corrosion inside a venting pipeline that conveys acidic gases. The objective here is to develop a coating inside the tubes that reduce the corrosion by 40% and increase the maintenance interval. The solution developed would benefit also in reducing the risks and the process safety, and it will, of course, save costs and energy consumption. The development of coating against thermal and chemical stress is based on using pre-ceramic polymer commonly named polymer-derived ceramics, as a base material. We can find multiple kinds of pre-ceramic polymer. In our scope, we focused on silicon-based polymers as polysiloxane or polycarboxylane. These polymers have the ability to convert into a ceramic with a thermal treatment. Depending on the nature of the polymer, the temperature, the atmosphere, and so on parameters of the thermal treatment, these materials can lead to silicon oxycarbides or even silicon carbide ceramic, for example. These materials are low cost and easily processable. They allow the tailoring of chemical composition of the ceramic at the step of synthesis of the polymer. They convert into ceramic at relatively low temperature, between 500 degrees and 1000 degrees. They convert into a ceramic glass, and at higher temperature, crystallization can occur. The main issue of these materials are that they have high weight loss, around 20%, and dimensional shrinkage. With this kind of polymer, into this polymer, we add ceramic fillers to act as a chemical barrier, anti-weighting, and modify thermal and mechanical properties. We can say that this mixture, this blend, can work as a ceramic matrix composite. The work plan is to formulate materials and to do inputs to the computation modeling that would help to determine specifications. The objectives of the coating is to have a good adhesion, a durability with no delamination during thermal cycles. It acts as a chemical and physical barrier, and the coating shouldn't have cracks and open porosity, and be inert with the liquid phase, the melted aluminum, or even the acidic phase. The thermal properties should be the closest to the substrate to avoid also thermal stresses. Two coatings were developed to match with the use case. For the case of aluminum foundry, the protection of refractory and graphite is done using the same coating formulation. Different deposition process were assessed by brush, deep coating, or spray coating. Thermal treatments are done in two steps. The first step is to cross-link the pre-ceramic polymer, and the second step is the pyrolysis at high temperature to convert the pre-ceramic polymer into a ceramic. To assess the performance of the coating, multiple tests are done, like adhesion testing by crosscut or pull-off testing. Microscopy analysis is also performed to assess the integrity of the coating, its thickness, and the presence of defects. This analysis is also done after the sample are immersed into melted aluminum by using a rotating device. For the second use case, the same procedure is performed, but for this case, a different formulation is developed to act as a chemical barrier against acidic gas carried inside the tube. Quantitative testings like electrochemical impedance spectroscopy is used. Here in the table, you can see results of the performance of a coating reaching a low corrosion rate about 4 millimeter per year. At CEA, a dew point test bench was also developed. This bench allows us to put sample into an acidic gas environment, similar to the use case. Then we assess the performance of the coating with measuring weight loss and do some microscopy. First, tests of scaling up the deposition process of the coating were done using robotic arm and automatic spray gun. This technique allows more reproducible deposition. The evaluation of the coating after thermal treatments are then compared to lab scale samples. The further developments focus on the assessment of the performance of samples that were immersed into melted aluminum. The new test bench of dew point that is more representative of the real conditions will be used to test coatings in acidic environment. And further development focus on the use of larger batch because work have to be done on the stabilization of the formulation. The use of additives is mandatory to limit sedimentation or agglomeration of ceramic particles. Developments with the other work package also focus on the integration of sensors to monitor the performance of the coatings when they will be applied in real condition. And yes, of course, to continue work on computation modeling to understand better the thermomechanical stresses. That's all for me. Thank you for your attention. And if you have a specific question, you can send me by email or ask your question right now. I do some advertise on my last publication. Thank you.
Thank you, Sebastian, for your presentation. So as said, if you have any question, do not hesitate in the chat. Okay, so we are going to switch to the following topic with Pilar on the innovative high temperature and creep resistance materials based on HEA models.
Thank you, Marie. Do you see my screen?
Yes, we will
Okay.
see Need a change?
Full. I'm going to change to full screen. Okay. So thank you, Marie, for the presentation. Thank you all for attending. So my name is Pilar Rey. I work in AIMEN for more than 50 years. And I work in the advanced manufacturing department. And I am the in charge of the work package 4 in ACHIEF project that deals with the development of high entropy alloys for high temperature applications. So our main target for this work package is to develop new high entropy alloys using atomization. So we want to get powder, and we will use AM processes, both PBF and DD, to manufacture and print these materials in order to be validated in energy-intensive industries. So I'm not going to introduce high entropy alloys because my colleague Tom did so. But the idea of using these materials is because they are outstanding materials. So we have a lot of combinations using the almost whole periodic table. So we can develop many different high entropy alloys. But the issue here is to develop materials with a specific function. And in this case is that they can stand high temperature conditions. So the idea is to have these new materials with high temperature resistance, not only strength, but also creep, and also to develop coatings with high temperature wear resistance. In parallel, another specific objective is to use atomization in order to develop these high entropy alloys powders that can be used for both process, PBF and DED, that they use different particle size distribution. At the end, with this both process, we need to determine the most suitable parameters in order to have a good quality for these materials, and finally to characterize these materials and to correlate composition microstructure with these high temperature properties. So this is more or less the work package 4 in the ACHIEF value chain. So this is the relation between our work package and the other work package. So we start with the development of the new materials using digital tools that Tom already explained, that are artificial intelligence, to create a list of suitable materials, but at the end, it should be supported by the simulation and modeling for select the most suitable ones for these high temperature conditions. Then we move to work package 4, in which we atomize these high entropy alloys for make these coatings, but also for create bulk material. And in order to compare the performance of these digital tools, we have also selected a high entropy alloy for the literature in order to compare the properties of both materials. And together with this, we have working here VTT to atomize the lab scale powder, and then we will scale up the powder through our partner synthesis. Once we have the powder, we move to the additive manufacturing processes. So we have here a CA that is in charge of the laser PBF process, AIMEN that is in charge of the DED laser base, but also for the laser cladding process, together with the mixing of the high entropy alloys with some reinforcement in order to get these high entropy alloys with some kinds of particles inside in order to increase the wear resistance. So the application of this process will be in two sectors. One is steel and the other aluminum. That these sectors are represented by in the case of steel by ArcelorMittal, and in the case of aluminium by Constellium. So in the case of Arcelor, we will create some parts for a reheating furnace. And the idea is to get or to improve the high temperature strength and creep resistance. And together with this, in this application, we will use sensors for the monitoring of the temperature and the strain. And we will introduce these fiber optic sensors in a coating made of with these high entropy alloys. In the case of Constellium, the idea is to apply these metal matrix composites based on HEAS in the rolls in the aluminum process in order to increase the wear resistance at high temperature. So in the case of the development of the materials, we select this one that was the first that we select, and is a high entropy superalloy. And the second one that was selected using these digital tools, we call medium entropy because it's 4 elements. But in any case, the approach is quite different. So the objective with the high entropy superalloy is to promote the hardening with precipitate gamma prime phase with the higher volume fraction, but also with a large diameter in order to increase the resistance. As opposite and with a very different approach, the objective with the artificial intelligence high entropy alloy is to promote a multi-scale microstructure. So our idea is to get 4 phases instead of 1 or 2, in which we have an FCC and BCC mixed with a B2 and I2 phase. So the first step is to atomize the powder. So as I mentioned, it was done in VTT. So they prepare the pre-alloy, they melt the elements and solidify several times to homogenize the composition, and they atomize batches of 15 kilos. But the issue here is that they have different fractions. The chamber fraction is the largest one, and these fractions should to be sieved into switchable particle size distribution for both processes, for PBF that use lower particle size and for DED, as you can see here. But the problem also that we have to disregard the cyclone fraction because it's very fine and it promotes the clogging of the nozzle and it's not usable for AM. Then we characterize the powder. So first we cut and polish the powder, and we make some EDX analysis in order to see the distribution of the elements inside the particle. And as you can see here in the first material, we have some segregation into the interdendritic region. And we have only one phase that is VCC. And in the other material, we have at least a most homogeneous distribution of the different elements that compose the alloys. And using EXRD diffraction analysis, we check that we have 2 phases, FCC, and BCC. Also, we perform some analysis in using DTA in order to know what is the behavior of these 2 alloys, both in air and argon, and we get some interesting results. Above all, comparing both materials in air, because with the first material we get some peaks here, but the problem is that these peaks are associated with a large loss of weight. That is something that we cannot see here in the second material, in which the peaks are associated to the oxidation, but with a weight gain instead of loss. This kind of DTA can be associated with the problems that we'll explain later during the manufacturing. When we perform this analysis in argon, the situation changes and this material behaves better, but in that case, with the state-of-the-art GEA, we almost all these peaks disappear, but we still have some weight loss because of some kind of evaporation. If we have a look to the particles with a scanning electron microscope, we can see the size that also was analyzed by using laser diffraction. But the issue here is to check the morphology of the particles, because for us, it's very important the sphericity of these particles in order that the powder flows correctly through the nozzles in the case of the DED, but in PBF, in order to record properly the powder. So so the morphology is quite good for both fractions, and the PCD is also quite homogeneous, and almost we avoid the formation of some satellites that are small particles attached to the big particles. Together with this, we prepare some mixtures, mixing one of the hairs with some particles in a turbulent mixture in order to avoid the destroy of the morphology of the particles. So if you have a look here, you see that with nanoparticles, we still preserve the spherical aspect of the particles, and that the powder flows quite well. So we have some penalty on the flowability as we increase the percentage of the nanotick, but in any case, they flow, and we were able to deposit some class on the base material. When we have a look to the cross-section of the particles, we see that the nanotick is attached, forming like a layer, like a coating surrounded the particles. So it means that the nanotick flow with the high entropy alloy. When we move to the process with the PBF and the first material, we get relative good bulk density, but the problem is that we get some network of small cracks that we detect using tomography and optical microscope. And these cracks are situated at the high angle grain boundaries following the joints of the solidification cells. So the quality is not as good as we expect at the beginning. And in any case, CA go further on the analysis and detect the presence of the gamma prime phase that was confirmed by XRD analysis. And after some thermal treatment, this gamma prime increase and it reached almost 50% of the composition. In DED, the results are completely different in the sense that also we have cracks, but these cracks are magnified because of the lack of chamber to protect almost the atmosphere. But it's not the only problem of the oxidation, because when we increase the protection on the nozzle, we get a better performance and a better quality, but in any case, we still have these cracks. And as you can see here, during the manufacturing, we detect some ejection of some material that can correlate it with the DTA. And this is a problem that is not only related with the quantity of oxygen that we have on the atmosphere. So because of this and the time of the project, we decided to go ahead at least for printing with the artificial intelligence high entropy alloy. If we move to this alloy, you can see here that the quality is completely different. With PBF, we reach almost, I say, 100% of the relative density, and no cracks were detected with this material. And now we are performing some thermal treatment in this material in order to promote this multi-phase microstructure in order to increase the resistance of this artificial intelligence material. For DED, what happened? As I mentioned, the quality is nothing to do with the first one, so we don't detect cracks nor porosity. And we were able to deposit some coupons here and to extract some tensile specimens. So as you can see, that the properties at room temperature at least are very good and with a very good compromise between the strength and the ductility. And okay, now we have in progress some further and deep analysis in order to go ahead with the to see exactly what is the microstructure, the phases. And regarding this thermal treatment, we also developed in this DD coupon, we cut and we make some different thermal treatments in which we change the temperature or the time, and we get some interesting results that we need to analyze more in depth. But for example, with high temperature, we detect that these recrystallized zones disappear, and we get well differentiated two phases. One is enriched in aluminium that correspond to VCC, and the other is FCC. But when we increase the time, we have also detect some precipitation phases here that probably corresponds with the B2 phases. But as I mentioned, deep analysis is being carried out. With the cladding, we test, we create some small batches, and we use different reinforcement, different type of these particles using titanium carbide as nano, but also with micro. And we change the laser power, the speed, the powder flow, and these are the gas flow in order to protect the oxidation, different overlaps. And with the micro reinforcement, we get better hardness, at least at room temperature, because with nano, we promote higher dilution, but the problem with micro is that we have a strong dispersion when we make this micro hardness test because of the different size of the reinforcement and the alloy. So the next steps for this work package is to go in deep and try to understand what is happening in the microstructure in as-built condition, but also to compare with the thermal treated material, and to carry out some tensile tests at high temperature, and to compare as-built with the thermal treated material, and also to develop some creep tests at different temperature and speeds, and finally to scale up this powder in order to develop the test cases in work package 7. And in the case of the laser cladding, we need to adjust a bit the process parameters, and also to carry out the high temperature wear test for the, let's say, best MMC coatings. So these are our colleagues that support me in this work package. That's all for my side. Thank you for your attention and for attending to this workshop.
Thank you, Pilar. So once again, if you have any question, do not hesitate to share them in the chat. And in order to be consistent with the planning, if there is no question, I propose that we take the opportunity to have a small break for those who need one, and to start with the following topic at 11, as it was initially planned. So we have one question for you, Pilar. Do you think that the number of HESA that could work are almost infinite, or that the two or three tested are more or less the only ones suitable for the application? It's a question from Ariane for the consortium use case.
Okay, so the number of combinations is not infinite, but is very large. But in any case, it's reduced when you think in our application. So there are high entropy alloys for hardness, for creep, for high temperature, for specific for corrosion. But for our application, obviously, is limited because we are looking for let's say a very specific conditions. So normally in high entropy alloys, you have 2 or 3 big families. One are the refractory that use refractory elements in the periodic table. The second one is the high entropy superalloys that we already tested. And the third new family is the ones that call the eutectic. So this limit the number of combinations that you may have. And at the end, for these materials, you look for elements that stand high temperature or phases that can stand these high temperature conditions. But the issue or the most tricky thing is the combination of the different elements and in different proportions or promoting different phases, because at the beginning, the high entropy alloys were defined as equiatomic and single phase, but now we know that there are materials that can be complex phases and with less elements, but they are still high entropy alloys. So yeah, the issue here is that we probably could test more than 2 or 3 materials, but the problem is the limitation on the time of the project. Okay. I don't know if I answered your question properly, but I hope so.
Excellent answer.
Thank you.
Okay, let's say that we keep the same idea of starting the following topic at 11. Okay, everyone. So welcome back. So we are going to carry on this workshop with the next subject that will be presented by Lorena Caliero from Tecnalia about advanced chromium steels with 15% improved creep resistance and high temperature corrosion resistance. Lorena,
okay.
I'll let you.
Thank you, Marie. Can you see my screen?
We see you, but we don't see your screen.
Okay. Now, maybe?
Yes, this is good.
Okay. So I'm trying to put on the screen. Okay, can you see the slides changing?
Switch to the following one. Yes.
Okay. Thank you, Marie. Okay, so good morning, everybody. My name is Lorena from Tecnalia, and we are going to talk about optimized chromium steels for creep resistance, which is the content of work package 5 carried out by Tecnalia and Tubos Unidos. The first objective is to develop novel chromium steel grades with improved creep resistance with respect to standard magnetic steel grades, those commercial ones, such as X20, P91, P92, and the reference steel finally selected in the project, which is T115. The second objective is to optimize heat treatment conditions for an improved control of the macrostructure and precipitates that can be formed, especially during the stage of tempering. There below, you have an example of the products offered by Tubos Unidos for oil and gas, chemical and petrochemical, power generation, heat transfer, automotive, mechanical, and construction industries. The case study we are targeting to involves 3 main centers, Tecnalia, Tubos Unidos, and Tupras, and contains an activity starting from the lab scale and finishing with the pre-industrial scale with the manufacture of pilot tubes for creep applications. The first target is to improve the energy efficiency of the boiler together with the oil refinery process efficiency. The idea is to obtain these objectives by using boiler steel pipes made of novel chromium steel grades that are provided with higher creep resistance and higher corrosion resistance. So the idea is to produce pilot tubes at the end of the project and test them in Tupras, which is the petrochemical refinery. Okay, here we have the main structure of the activity carried out within this work package, starting with the dilatometry study, going through lab scale activity, and finishing with the pre-industrial scale for the fabrication of the pilot tubes. So we start with laboratory castings of the novel chromium steel grades, and then we forge this material into bars, and these bars represent the material of the samples we are going to use in the dilatometry and lab scale studies. And these studies aim at selecting the best steel and the best processing route to be reproduced later on at pre-industrial scale for the manufacture of pilot tubes. Let's start seeing the laboratory castings. We have performed laboratory ingot castings of 4 new chromium steel grades with compositions previously designed in the project. So we have produced 4 ingots of 30 kilograms at lab scale, and we have also produced by casting at lab scale the reference steel T115 for comparison. Then we have analyzed the compositions of the 5 steels to ensure that we have obtained the targeted ones, the designed ones, and then these ingots have been forged into bars of 45 millimeters in diameter, as we can see in the picture. And these bars is the material we use for the following studies, as previously said. We are going to perform 2 studies, dilatometry study and a lab scale study. We take a first set of samples from these 4 bars to accomplish the dilatometry study, in which we design and apply different processing routes to different steel grades to see the effects. So we characterize then the samples, and based on the results obtained, we decide the optimum processing route for each steel grade. And then these optimum processing routes are applied at lab scale on the steel grades, but using the same material but of higher dimensions. This is why we call it a lab scale activity. Okay, let's see what we have carried out within the dilatometry study. We have started with the application of a normalizing treatment on the steel grades in order to have enough information to be able to calculate the critical temperatures of each steel grade. And then with this knowledge, we are able to design the thermal treatments most suitable to each steel grade. Okay, so then we apply them, we characterize the samples, and based on the results obtained, we select the best thermal treatments for each steel grade. The thermal treatments applied are 3 thermal treatments. The standard one, which is similar for all the steel grades and is based on normalizing and tempering, and then 2 innovative thermal treatments, TT2, that are also based on normalizing and tempering treatment, but interpreted with a Martin sensitization step in between. This Martin sensitization step can take place at MT10 temperature to retain 10% of austenite, or at MT30 temperature to retain 50% of austenite. But in order to do so, first of all, we need to calculate the Martin sensitization temperatures, MT10 and MT30, for each steel grade, because these temperatures depend on the steel grade composition. So once we get to know these temperatures for each steel grade, we have enough knowledge to apply successfully these 3 thermal treatments. Let's see the microstructure of the different steel grades after the thermal treatments have been applied by dilatometry. The first picture corresponds to the result of the application of the standard thermal treatment to each steel grade. And then the second and the third pictures correspond to the result of the application of the innovative thermal treatment 2 with MT10 temperature and with MT30 temperature. In global terms, we can say that for all the samples, the standard thermal treatment and the TT2 with MT10 temperature give rise to tempered martensite with imperial austenite grains of different size. In the thermal treatment 2 with MT30 temperature, tempered martensite and fresh martensite are formed with imperial austenite grains of different size. In sample V2, for the highest MT temperature thermal treatment 2, very angular tempered and fresh martensites are observed. And in the case of samples T115, V1, and V3, we can observe ferrite traces decorating the prior austenite grain boundary of the macrostructures when applying the high MT thermal treatment 2. So these are the main aspects to highlight at macrostructural level. Let's see what happens when we measure biggest hardness on the dilatometry samples after thermal treatments. For all the steel grades, the introduction of a Martin sensitization step increases the hardness, and this happens especially for the higher MT temperature, that is MT30 versus MT10, due to the fact that when we stop at a higher temperature, we apply the Martin sensitization step at a higher temperature, we are retaining more austenite, and this means that we can obtain more fresh martensite after temperature. Based on hardness values, the higher MT thermal treatment, that is TT2 MT30, was selected instead of the lower MT thermal treatment, TT2 MT10, to be applied at lab scale. Additionally, the standard thermal treatment, TT1, was applied at lab scale to all steel grades for comparison. So we have selected these two thermal treatments, the standard one and the innovative one with MT30 temperature. And these selected thermal treatments are called the optimum processing route and applied on the steel grades at lab scale. In order to do so, we need lab scale samples and lab scale processing facilities. The lab scale samples used are cylinders of approximately 45 millimeters in diameter and 100 millimeters in length, which is the second set of samples taken from the forge bars. And then for lab scale processing, we use facilities such as muffle type furnaces and a salt pad installation. Okay, after lab scale processing the lab scale samples, we need to characterize their macrostructural and mechanical properties through different techniques. The idea here is to obtain enough information to be able to select the best steel grade, that is the best composition and processing route, which will be the one offering the best overall creep behavior. And the target is to take this best choice and to reproduce its fabrication at pre-industrial level for the manufacture of pilot tubes for creep applications that will be then validated in the project. Okay, so let's see the characterization of the lab scale samples after lab scale processing. Remember that we have an amount of total amount of 10 lab scale cylinders because we have 5 steels with 2 thermal treatments. At lab scale, the macrostructures obtained are more or less similar to those observed at the dilatometry level. In the lab scale, the thermal treatment 2 gives rise to larger parallel austenite grain size in comparison to the standard thermal treatment. And we can also obtain fresh and tempered martensites in the steel samples. The scanning electron microscopy study confirms the predominance of a martensitic macrostructure in all cases, with niobium precipitates in those steel grades with niobium in their composition. The X-ray diffraction analysis shows a similar pattern for all the cases with the predominance of a martensitic macrostructure in all the steel samples. When we measure the tensile properties and hardness at room temperature for those lab scale samples after lab scale processing, we can see an increase of the properties when going from thermal treatment 1 to thermal treatment 2 in samples V1 and V2, in accordance with what happened at dilatometry level. Let's see what happens with the corrosion properties of the samples. Here, first of all, we need to take into account that the reference steel we are basing on, which is T115, is really good at corrosion. Okay, so when we change its composition, creating V1, V2, V3, and V4, we do it with the aim of increasing creep resistance. Okay, so if we manage to increase creep resistance while preserving the corrosion resistance of the reference steel, that would be a very, very good result. For the moment, the study says that the mass increase observed for all cases can tell us that we are seeing a similar behavior for all the samples, but with the exception of the sample V2 for thermal treatment 1 and thermal treatment 2. But the rest of the samples behave more or less similar to the reference steel, at least in terms of mass increase. The creep test carried out at 3 different stress values can be divided into 3 types of tests. In red, those that have been finished. In black, those that are still in course with still room for elongation improvement. And there is another set of tests that have not been started yet. Okay, so if we focused on the highest stress values, first of all, on the creep tests that are finished or almost finished. And then we take into account those that are processed at higher stress values. In case of thermal treatment 1, we can say that the samples that show a best behavior are V1 and V3. And in the case of the thermal treatment 2, the samples with the best behavior are V1, V2, and V4. And this is the stage of the project at which we are right now. So we need to finish those creep tests to obtain enough information of the characterization and properties at lab scale to be able to select the best steel grade. That is the best composition and processing route, which will be the one offering the best overall creep behavior. And this best choice will be then reproduced at pre-industrial scale for the fabrication of pilot tubes for creep applications. Let's see the activity to be carried out at pre-industrial scale. We are going to perform 2 pre-industrial castings. So we are going to produce 2 pre-industrial ingots of 700 kilograms each. One of the best candidate steel grade, previously selected, and then the reference steel grade for comparison. Okay. So then after producing the 2 ingots, we measure the chemical compositions to ensure that we have obtained the designed ones. And we start working with these 2 ingots. What we are going to do with these ingots is to use them to fabricate pilot tubes. But in order to do so, we need to adapt and implement at pilot scale the thermal treatment route defined at lab scale. And we will also need to include the hot rolling steps. So the target here is the production of those pilot tubes for creep applications to be validated later on in the project. Okay, at pre-industrial scale, we have started with the pre-industrial castings of the reference steel with good results in terms of composition. Now we are focused on the stage of processing this material, machining, rolling, and the application of thermal treatment at this pre-industrial scale. As future work, as said, first of all, we need to finish the creep test to have enough information on the properties of the samples at lab scale to be able to select the best steel grade. Remember that this means best composition and best processing route, and which will be the one offering the best overall behavior, but we are focused on the creep behavior. Okay, this is the key property. And then this best choice will be reproduced at pre-industrial scale for the manufacture of those pilot tubes that will be validated later on in the project in terms of properties, but also with pilot test and tube press. And I think that's all. So thank you so much for your attention.
Thanks, Lorena. Do we have any questions following this presentation? Okay, so it seems no, but in case we have afterward, I will share them with you. So to finish, we have the last topic that is going to be presented by Britta concerning sensor developments with the ability to withstand harsh environments.
All right. Hello to you all. I hope everything is. That's perfect. Thanks, Marie. Yes. My name is Britta Koch. I work in the research and development team at Enionic Fiber Optics. And first of all, I would like to pass on Andreas Pulkötter's sincere apologies for not being able to join us today. And he has asked me in his stead to present our talk today, sensors development with the ability to withstand harsh environments. So first of all, here you see a schematic of the materials development group that we proposed in ACHIEF to not only develop high performance materials and components, but to also complement their performance with sensor functionalities and test them in 3 different use cases. So you've heard today in our talks that we have 2 different sets of materials that we plan to develop here, the high entropy superalloys, where the artificial intelligence aided modeling step first gives us prominent candidates that are then actually fabricated at AMIN. And we also have the polymer derived ceramics that also can serve as embedding material for then sensors that are to be implemented at the use case sites. We at Enionic Fiber Optics fabricate fiber optic sensors that can be used for temperature and strain measurements. And these sensors are to be applied at the steel use case site and the aluminum use case site. AMIN as well is developing an electrochemical impedance sensor that is to be tested at the petrochemical use case site. And with this, before we actually delve into the results, I would just like to highlight here that I show results today for this first approach. We're halfway through our work package, and I can share with you some preliminary results on this today. First of all, I would like to introduce the basic principle, the operation principle behind the fiber optic sensors for you to understand better the considerations that we had to take into account when we actually designed our next steps. So we use fiber Bragg grating sensors. These are modified optical fibers. Basically, you all know from the telecommunications industry. This is how hopefully you soon receive your internet connections, and we augment these optical fibers with a periodic modulation of the refractive index. And this gives them an added functionality to have an optical mirror. And if you then illuminate the fiber with a broadband white light spectrum, the wavelength of the light that is in resonance with this periodic modulation of the refractive index then gets reflected from the structure. So you get a reflected spectrum with a specific so-called Bragg wavelength that is missing in the transmitted spectrum. And this behavior of the optical fibers changes if you add some physical properties to its environment. So you could either heat it up or stretch it. This affects the periodicity, so the distance between the periodic index modulations, and that then results in a shift in this Bragg wavelength that gets reflected. So whatever physical quantity impacts the expansion of the fiber, or as this is the case for temperature, also has an impact directly on the refractive index of the material, then can be detected in this wavelength shift. We can easily reach resolutions with the sensor for temperature for 0.1 degrees Celsius, or a microstrain can also be measured with these type of sensors. So at Enionic Fiber Optics, we achieve these periodic refractive index modulations with the point-by-point inscription method. So we use a femtosecond laser source and basically shoot defect size in a point-by-point manner into these optical fibers. These are commercially available optical fibers, and the advantage of our fabrication route is that we do not care so much about the coating material, as the infrared laser usually passes through the coating without any harm. So we can prepare very customized and well-defined fiber break gratings. Sorry. When we discussed together with Eamon how to best embed the fiber optic sensors in the HISA material, this is the proposed route that we came up with in the beginning. So first, we thought we would have to remove the polymer coating that usually is around commercial fibers to protect the fiber to make it not as brittle, inscribe our fiber break grating structures into it, subsequently coat the fiber with metal for good thermal conductivity, and also to protect the fiber again at the high temperatures where polymer materials no longer would work, they would just burn away. And in the last step, embed these sensors in the high entropy superalloy material. For temperature measurements, that is shown here on the top right-hand side, we need to make sure that the optical fiber actually is loosely mounted inside the material to make sure that any strain effects that arise due direct physical contact do not impair our temperature measurements. So we propose to actually mount it in a capillary tube, and that then leads to a thermal equilibrium with the surrounding material. For the strain sensing, we propose to actually bond the HISA material to the metallic coating that is around the FBG sensor fiber. And we thought we could either achieve that with a thick enough metallic coating or with an intermediate microcladding coating step to make sure that the fiber is not harmed through the additive manufacturing step. So walking you through the different single results that we got. First, the decoating of the fibers. Here we set up an array of etching baths to remove the polymer coating of commercial fibers. And the difficulty here is that the bare glass fiber is quite brittle without the coating. So we had to find a way to make it in a continuous but also careful manner. And you see here that there is the removed coating from the fiber. Depending on the type of coating, you can use different etch baths to make sure that you clean the fiber properly. In the next step, we wanted to test the FBG inscription. That's a standardized procedure at our company. However, we were not sure if that also would work if we directly would try to write into the fibers. You see here, for example, microscope images of the polymer coated fiber, a carbon coated fiber, and a metal coated fiber. We need the carbon coating because we need a way to actually deposit then the metal onto the fiber. You've seen that in the schematic layout of our experiments. And the carbon is weakly conductive and supposed to help our metal deposition after the FBG inscription setup. So we thought we actually would also test metallic covered fibers here. If we could directly write into these fibers, that would save us a processing step. However, the setup relies on optically detecting the core of the optical fiber. You can see that for the polymer coating, we could nicely see through the fiber. The carbon coating decreases to some extent the amount of light that actually gets shone through. However, for the metal coating, of course, the detection algorithm does not work anymore. So we actually settled for the bare or the carbon coated fibers for the fiber break grating inscription step. Some parameters needed to be tuned. As you see here, that the carbon coating also can get damaged during the femtosecond laser shot procedure. However, we managed to find a nice set of parameters that actually works for our purpose. And here are some first reflection spectra from different optical fibers with break gratings inside. In the top row, you see 3 different gratings inscribed one after the other. The bottom row is a single FBG structure inside a fiber. We have here carbon-coated fibers, and for the metal-coated fiber here, we actually etched the fiber in the area where the FPG was to be inscribed. So for both types of fibers, we managed to write the FPGs into. However, the metal coating again needs an additional processing step. So we settled for the carbon-coated fibers for further experiments. So some further sensor characterization experiments here. Here we expose the FPGs to a defined set of temperatures up to 700 degrees Celsius and look at the wavelength shift that occurs at the in the reflection spectrum. On the bottom left corner, you see that there is pre and after annealing at the 700 degree, a shift in the Bragg wavelength that can be to a larger or to a smaller extent, depending on the FPG area. And this drift is well known in temperature. It results from relaxation processes within the optical fiber and cannot be get rid of at these high temperatures. However, this drift, you see here, the negative drift over time decreases a lot over time and can be taken into account numerically. So again, we prove the necessity for drift compensation with the sensors, but that is a well-known issue and can be taken into account of in the experiments. For you to give you an idea, 10 picometer per day roughly result to 1 degree Celsius. So this drift in the beginning is in a relevant area that diminishes over time to be basically neglectable. Next step now is to coat the fiber, the carbon-coated fiber with a protective metal layer. This is necessary, as I mentioned before, because the protective polymer coating that is around commercially available carbon fibers as well does not withstand temperature above 350 degrees C, and we have higher temperature use cases here. So also the carbon coating alone is not robust enough to withstand these industrial environments, so we need the metallic coating. And this has been achieved by AMEN with an electrodeposition technique. They chose nickel as a first candidate to coat the fiber with, and I learned that that basically is the gold standard of metal you choose if you want to coat something in this type of application. So they went ahead with nickel and nicely were able to also deposit different thicknesses, 500, 750 micrometer of metal coating around the sensor. So again, we were curious if the sensors actually did continue to perform well, and exposed them to a thermal fatigue test. That means cycling the temperature over an extended amount of time. You see here for 2 months, we cycled them at intervals between 200 and 800 degrees Celsius and observed if the wavelength shift nicely follows this temperature cycling. And you see here overlaid different metallic coated fibers for comparison, where in a first experiment, we were curious about the performance of these sensors after the metal coating. And what looks here on first glance maybe a bit unspectacular is really an achievement of its own, because the we have here a sandwich structure of a glass fiber, a carbon coating, and a metal coating, where we have no adhesion layers in between, but the cycling layer here does not destroy or delaminate any of the coated layers, and the fiber optic sensors still work nicely even when we cycle them over nearly 3 orders of magnitude. So we were very happy to see that the sensors were still working, and we now need to confirm that this is reproducible and also define which exact metal coating and also which alignment or which fibers to connect these sensors with then shows the best and most stable results. Now you undoubtedly are curious to see how the sensor embedding works and if we manage to actually enclose them in or embed them in the HESA material, but I will have to show you these results in 1 year's time. We'll have to be a bit more patient with that. So this is the outlook. We will, in the next step, use additive manufacturing to actually embed the fiber optic sensors with the metal coating in the HESA. And here I've shown you the remaining steps for our work package, and that is to actually validate the reproducibility of the results, continue with or finalize the thermal fatigue tests, and also develop a more continuous mode to actually coat the carbon coated fibers with the metal coating to go to larger scales. We then, as I showed you on the very first schematic slide, would like to actually use the HESA embedded fibers in the steel use case, and therefore would like to use the materials that are developed in other work packages and identified as the best suited candidates, and mount the sensor or configure the sensor in a way that it can actually be included and incorporated at the Arcelor steel use case site. With that, I would like to thank you for your attention and your interest. Thanks to the European Union to fund this research within the Horizon 2020 Research and Innovation Program, and I'm happy to take any questions.
So we have one question for you. Could it have been possible to use thermocouples for such applications?
Mm-hmm.
Can you please summarize the pros and the cons of optical fibers compared to thermocouple?
Mm-hmm. So thermocouples, that's basically the electronic way to measure temperature, and we pursue here the optical way, so use light instead of current to detect temperature. And thermocouples suffer the advantage that they do no longer work at very high temperatures. In the temperature cycling data that I showed you, we actually had a thermocouple present that then stopped working reliably above 650 degrees C. So we get here to extreme temperatures, and that's where the standard sensor equipment setup does no longer work reliably. And the advantage of optical sensors is that they are independent of electromagnetic waves, because they use light as the detection agent, basically, instead of current. And we have the glass fiber here that inherently is able to withstand high temperatures. So that's one of the main advantages that we have with the optical sensors. We have basically inert measurement setup. So with the light, we can install very easily larger arrays of sensors because we don't need the electrical wiring with each of the sensors. We can multiplex them one after the other and cover larger areas with it. So that's another set of advantages here.
Thank you, Britta. So we come to the end of our workshop and conference. So first, I would like to thank all the partners, so Tom, Sebastian, Pilar, Lorena, and Britta for their intervention today and the quality of their presentation. I would like also to thank Raquel for the organization, our support, and all the communication that have been done for this workshop. And so just to let you know concerning a brief summary of the next steps of the project. So to finish the project, so we will have to validate all the materials at lab scales, to implement them also with the sensors in the 3 different use case. Following this step, we will validate the novel materials at Arcelor, Constellium, and press plants. And if the results are positive and relevant, the goal will be to exploit the different results in order to be deployed in the other energy-intensive industries, and in order to, as I remember, to attempt the different objective, meaning decreasing the energy efficiency by 30%, reduce the CO2 emission by 20%, and also to increase the equipment lifetime by more than 20%. So we have a lot of nice challenges to be part of the objective of the European Commission. I would like also to thank you all for following our conference. I hope you have learned nice information, and that you have been interested by the content of this project. Do not hesitate, if you have a question afterward, to share them with us. We have also registered the meeting, so it will be available after if you want to review it, and also if other question or remarks come to your mind afterward. We are really open and happy to communicate with you. And here you can have the mail address for any communication, a reminder of our website, and for sure we use also a lot Twitter and LinkedIn for any news about the project. So that will be the last word for this meeting today. So once again, a big thank you for everyone for participation, presentation, and organization. And if I make a last check, sorry, to see if there is no additional question. And as no additional question, once again, I wish you a nice day. And do not hesitate to come back to us for any question, and then we will share also the link to review this conference afterward. Thanks, everyone.
Thank you, Marie.
Thank you, Marie. Thank you, Raquel. Thank you all.
Bye-bye.
Bye.
Bye.
Bye. Thank you all.
Thank you, Marie. Bye-bye. Thank you all.